Welcome to Power Supplies Regulated Part 4. All right, in our previous video, we solved for C1 and the diode, the big filter cap and the diode and the specific part numbers. And we found that we had some issues with R1 and R2, R1 being a non-standard and a fairly high wattage at over a half watt in that position, and then R2 for sure was the standard value, but it was 3.5 watts. And so we're just very inefficient. It's inefficient to lose a lot of power within your regulation circuit, and then B, though that is an expensive part, it's a big power resistor. And then additionally, we found that PQ1, the power for Q1, exceeded the capability of a 2N3904. Not like big time exceeded, not even close. So in this video, we're going to see if we can't fix that and figure out a better way to solve for R1 and R2. All right, so to solve our 2N3904 problem, we're going to take a look at this transistor. It's called the TIP41. I got the data sheet here, so you can see there's two different power dissipations here. We've got 65 watts and 2 watts. And what that 2 watts is the dissipation in air temperature, basically in room air, meaning that there's no heat sink. But if we put a heat sink on this thing, we can dissipate up to 65 watts. So in our example, we're looking to dissipate 3.3665 watts. So we can handle that all day long as we put some kind of heat sink on that. The other issue here is we go further down. We may remember from second semester that HFE is equivalent or is the exact same thing as beta. So we've got two HFE listings here where VCE is equal to 4 volts and IC is 0.3 amps. And VC is equal to 4 volts where IC is 3 amps. And it says basically we're going to be anywhere between a beta of 15 and 75. And usually for TIP 41s, I just use the number 50 to calculate the beta. Okay, so the TIP 41 solves our problem of being able to handle the power, but it kind of induces a new problem because it's got a lower beta than the 3904, which means that the base current is going to be even higher, which means that the power for those resistors actually went the wrong way. Our R1 and R2 are going the wrong way with less beta. So a lower beta actually increases R1 and R2 power. So we're going to take a look on the next slide and see how to fix that. So here is, because we need a heat sink, I went on to Mouser and Googled heat sink for this part. And what you need to know when you're looking for heat sinks for these parts is the package type. And the TIP 41 is in the TO220 package. And so I just add that into heat sinks TO220, and it gave me a list of them. And there was a variety in this company. You can kind of see the list here. And I just went through and looked at the cost. I like this shape. It dissipates a little bit more heat, so that equates to power dissipation. And I just looked up whichever one, and you can kind of see the 635 here, the last one on the list. It required a bulk order, so I don't want to do a bulk order. I just want to order one. And really, we're only dissipating 3.366 watts for this circuit compared to the full capability of 65 watts. So the next thing I did was I just looked at the next one up. It looks like the next two up from there, the 508 and the 381, can dissipate 9.3 and 9.9 watts at 75C. And I looked at the price difference between those three, and I found the one that looked like, you know, it was probably the best out of both worlds, and it wasn't that much more expensive. I've got the price list on the last slide. But to me, I'd rather be able to dissipate a little bit more, or maybe pay like a slight amount more just to keep the heat off my parts and get rid of it, than to save a little money and put a little tiny heat sink on and run the whole thing a little bit hotter. So there's the part numbers that I kind of settled for this project right there. Okay, and getting back to dealing with the low beta of the tip 41, what we're going to do is add a Darlington, what's called a Darlington pair. You may remember this from second semester, but basically Darlington pair is a multi-stage current amplifier. So what we're doing is we're getting that current way down, and then the beta is just like in voltage amplifiers, multi-stage voltage amplifiers, the betas multiply. So it's going to allow us to get that base current down quite a bit so that we can then, that'll help out our R1 and R2. And in the next slide, we're going to see how that works. So here's our Darlington pair put into the circuit. Again, don't freak out because it's tipped on its side electrically, or the connections are all the exact same. And now we can start solving. We know that we want to look at the power calcs first for Q2. So we know the power calcs for Q1. 3.3665. That didn't change because the current is still 0.5 amps, and the VCE is still the same. It didn't change by adding the Darlington pair. The VCE didn't change across Q1. So our 3.3665 watts is still what we've got on Q1, and the tip 41 can handle that all day long with the heat sink. Now we want to figure out, you know, what is the power on a Q2. So, and I know it says 2 and 3904 there already, but we don't know for sure yet. We got to calculate that power. So the way to do that is to find the emitter current of Q2. So we're going to take the 0.5 amps on the output, divide it by beta plus 1 for Q1. That gives us the current at the emitter, and then we're going to take that current and multiply it by the VCE of that Q2. And again, normally power for the transistor is IC times VCE. So when I use IE, I'm just kind of padding it a little bit so that when I design or when I order my part, or get my part, I know that I'm even better than what I calculated. It should be just less than what I calculated. And so let's see here. We get a VCE. The other thing to consider here is for the VCE, we've got our 41.733 volts up here on the what we're calling the VCC up here on this rail here after the diode and the filter cap. And the difference between this trend, the Q2 and Q1, is there's an extra VBE for Q1. So when we Kirchhoff that out, we're actually subtracting 1.7 volts plus the 35 volts. So we end up with a voltage of, for VCE, of 41.733 volts minus 0.7, that's the VBE of Q1, minus the 35, that's your V out, and we end up with a VCE of 6.033 volts. Multiply that back by the IE of Q2, or you could use IC of Q2, and we end up with a PQ2 of 54.7977 milliwatts. And a 3904 can handle that all day long. So we're good to use the 3904 in that position. Okay, so now we can work on dialing in the R2 value. So we've got the 3904 in that Q2 position. We're going to now divide that. We're we're going to run everything at max. We designed these circuits with max current. And so we've got our 0.5 amps divided by 51, the beta plus 1 and the Q1, divided by, again, to get to the base of Q2, divide that by 101, the beta of Q2, and that gets us the IB of Q2. Okay, and it looks like we've got an IB Q2 of 97.069 microamps. And there's where you can really see the benefit of the Darlington pair. It really gets that base current way down. And so now we know that IR2 needs to be a minimum of 10 times that. So now we're talking an IR2 of 970 microamps. So not even a milliamp. Okay, and so, well, what's the voltage across VR2? So we added another transistor, so we've got one more VBE in there. So our VR2 is equal to 36.4 volts. So we divide that by the 970.69 microamps, that current, which is 10 times the IB of Q2. And that's just making sure that we're going to be rock solid stable for our VR2. And we end up with a 37.499 K ohms. So again, because we want to be a minimum of 10 times, if we round that value down to the next standard value, that just gives us, it gives us just a little more than 10 times, which makes us even more stable. So we're going to round that down to the standard value of 36K for R2. All right, so now that we've got R2, we know what R2's voltage is. It's the 36.4 volts. We need to divide that by now the standard value to get our actual IR2. And that gives us the 1.011 milliamps. We also need to find what VR1 is going to be. And that's going to be the VCC, the 41.733 volts minus the VR2, 36.4 volts, giving us a 5.33 volts in that position. Now we add the IR1 is equal to IR2 plus IBQ2, and that gives us a current of 1.108 milliamps. We divide that into the 5.33 volts, gives us a hard value. Now this is we can't round this to the next standard value. We get the hard value of 4.812 K ohms. So that needs to be pretty much exact what we calculate, or it'll adjust or change our biasing. Okay, so we did all this work. We added the Darlington pair, which we can see already that it's really lowered that current through that branch. So let's find the actual PR1 and PR2 values and see if we helped ourselves out and see what the difference is between the non-Darlington and the Darlington. And we can see that for PR1, we're just going to take VR1, which we already calculated, times IR1, which we already calculated in the previous slide, and we end up with a 5.9 milliwatts for PR1. So almost like nothing. That is so low. I think we went from above a half watt, 600 and something milliwatts, all the way down to 5.9 milliwatts in that position. For PR2, we've got VR2 times IR2, which we calculated in the previous slide, and we end up with 36.804 milliwatts. So we went from 3 something watts to 36.804 milliwatts. So you're talking like quarter watt resistors in that position all day long. So awesome. So I looked up on Mouser and I've got the prices here. I actually found a 4.81 K ohm resistor that you can buy. It's a little more expensive, 35 cents, compared to the standard 36K at 250 milliwatts at 10 cents. But I've also got the heat sink, and basically here's my parts list, parted out.